Welcome to 2024 spring semester forensic chemistry. I'm pretty excited about this course, and I know that you are too. Many of you have waited your whole chemistry degree program here to take this course to learn more about how chemistry is applied to forensic science. And what do you know? We get to the beginning of the semester and they cancel class because of the cold. So I hope that you're staying warm. I am too. Got a fire going in the fireplace, and I just didn't want to lose this day where we can go through the syllabus and get a brief introduction to forensic chemistry. So I thought I'd go ahead and record the first lecture, put it up on Blackboard so that we don't get behind. If we get too far behind in this course, then we have to cut things that are fun, like the tour of the police department or guest speakers. So in order for us to have those nice things at the end of the semester, let's stay on track. Let's go ahead and do this introduction and syllabus walkthrough. So here's the syllabus. You can download one from Blackboard. If you haven't got that yet, go ahead and stop the video, download the syllabus, have it up on the side or print it off, and you can go through it with me this morning. Okay, so the book that I really like for this course is Suzanne Bell's Forensic Chemistry. I used the first edition and the second edition, and then she didn't come out with a third edition for quite a while, but now it's out, and so this is the newest book in forensic chemistry by Suzanne Bell, and I really would like for you to get this book. All of the lecture notes and everything come from this book, and so it'll help you understand the science behind what I'm putting out in the PowerPoints. If you can't get this book right away, there's a few chapters of the second edition book that are available on Blackboard for download, just for your temporary use until you get the third edition book. These are all of the ways you can contact me. Email is preferred though, and I would like for you to start using the Outlook appointment, what do we call it? Sending me Outlook appointment requests. You can do that in Outlook by setting up a meeting. And then when it says attendees, you can look me up. And when you look me up, you can see my schedule in Outlook. It's called the meeting scheduling assistant. That's what you want to look for up on the toolbar. And this scheduling assistant will show you where I have openings in my schedule. And you can put a 30-minute slot in there and hit send, and then it will ask me if I want to accept that meeting. And if my calendar is accurate, which most of the time it is, I'll accept that meeting, and we can set up a face-to-face meeting, or we can meet via Zoom. So I want to make it convenient for you to talk with me and to get your questions answered. Of course, my office phone is there too. For quick questions, email or office phone is good. Our homeworks are due on Saturday nights, and so it's probably not a good idea to try to catch me on Saturday. A lot of times I'm traveling, and so I won't be able to help you out. So make sure you start the homework early and ask all your questions on Thursday afternoon, Thursday evening, Friday morning, Friday afternoon. Then I can help you with those homework questions. And then always form study groups and get together and learn from each other. Okay, as far as assessment is concerned, we're going to have some homework, some control charts, and exams. The attendance is not recorded. I'll record it on the roster, but it's not graded. So I don't need doctor's notes or anything like that. I put attendance and engagement really down as a reputational score. What does that mean? Well, I'm really eager to see that you're interested in the course, that you show up at 8 a.m., that you contribute, you ask questions in class. If you disappear, I'll see that on the roster. And so occasionally, for whatever reason, students will stop coming to class, and that leaves a sour taste in the professor's mouth when they don't see you, and then all of a sudden you have questions. They don't know who you are. So come to class regularly, and I'll keep track of that. But again, there's no points associated with it. As far as the exams, they'll be mostly multiple choice with a few written examples, just like you saw in PChem. Nothing's changed from that, except for the note card. I think that this course is a lot of vocabulary, and I really want you to commit it to memory. And so I don't want to allow you to have a note card where you can just write everything down on a note card and then just copy it onto the test. Then you're not really learning anything. It's not getting into your head. So I will provide the equation sheet along with the periodic table so that you won't need to write any equations down, but you'll need to have all of the text and the note, the vocabulary and so on committed to memory. As far as makeup exams, we really don't do makeup exams. If there is an excuse, if something's happened in your family or life where you can't make the exam, we can work something out in terms maybe counting the final for that missing exam average or what have you. So I'll work with you, but you've got to actually be sick or absent. Homework is due Saturday night, just like it was in PCHEM. It'll be a multiple choice test or fill in the blank on Blackboard. You get 2 attempts, and again, don't wait until Saturday afternoon or Saturday night to turn those in or to start them, because if you run into problems, you'll get a 0, and it won't be because you don't know the material, it'll be because you procrastinated and waited too long to turn it in. Something new for forensic chemistry that I didn't have in PCHEM is this control chart exercise. We'll talk more about it in a minute, but you will choose a process to monitor daily the whole semester. And then it's also due. The data will be entered each week, so 5 days at a time or every day, into a common spreadsheet. Everybody will have a tab. So you'll go to your tab and you'll enter your latest data into that spreadsheet, update your chart, and then I can go through and look to see that everybody's submitted their data into this one master spreadsheet and give you some completion points throughout the semester. And then we'll have a midterm quality report where you analyze your control chart and you write up your conclusions, and then you will get some feedback. This will be the first time I've allowed peer grading or peer evaluation, peer review. And so 2 of your peers will read your midterm quality report and give you some pointers on how to make it better. And then your final quality report will have a comment response table where you take those comments that were given to you by your peer reviewers and you address them in your final quality report and turn that in. Okay, attendance. Again, I said that lecture attendance is recorded each day by signing the roster. Again, even though there's no points associated with it, I keep track to see who cares enough to show up throughout the whole semester, and also to detect if anybody is checked out and quit coming to class. Also, responsiveness is critical in the real world. So if I'm sending you emails and so on, and you become unresponsive and don't reply back, or you reach the storage limits on your campus inbox or what have you, these are kinds of things that you would need to fix if you were working in the real world. And so I want you to fix them here. I'm trying to train you to be responsive and be responsible for the next thing, for the job market. Okay. And so that's why some of these rules are in place. Now, academic dishonesty is not really a problem most of the time, but occasionally a student or two cuts a corner and they end up ruining their chances of working in the crime lab. So your reputation takes a lifetime to build, but can be destroyed in a few seconds or with one poor decision. So start holding yourself to the highest ethical standards that you can. Okay. Don't sign a roster for friends. Don't use stolen copies of exams, etc. And so just hold yourself to a high standard, because that's what we need for forensic scientists and everybody, to be honest. Okay, this is just some further disclaimers, but also a note here that I'll only write recommendation letters to forensic programs for students who make A's in this course. Again, when I'm writing a letter, I'm trying to sing your praises, and it doesn't work well if I'm singing your praises and I say, oh yeah, but they were a poor student and they made a C in my class or what have you. So that puts me in an awkward situation. And so it also puts you in an awkward situation. You don't want a letter where someone highlights a poor grade. You want a letter where someone talks about all of your positives. And so let's aim high. Let's get into the course now. This is the full schedule for the course. You see there's 3 sections. There's equality requirements, chemical evidence, and physical evidence in the course. It's organized by weeks, just like PCHEM 1. And each week folder in Blackboard will reveal, I think it's on Thursday evening or Wednesday evening, it'll pop open for the next week's lectures. I have some partially filled out PDFs that you'll download, and you can go through the class notes in class, print them out 2 per page, and you'll be able to make a notebook with all of your notes in it. The weekly homework quizzes I'll do on Saturday nights, and there's one for every week. And then there's an Excel exercise, and then your midterm quality report and your final quality report. Also not shown here is the weekly updating of your control chart data. So that's a weekly skill. After I approve which data source that you're going to be tracking, then you can begin tracking. So we probably won't have our data sources approved until probably the second week. So I want you guys to be thinking about what you're going to track, and so we'll get that started week 2 or maybe week 3. Okay, so let's go through a brief introduction to forensic chemistry. This is science applied to the legal requirements, or science applied to law. And as with personal protective equipment like gloves, they protect you, okay, but they also reduce your dexterity to some degree. And you may have noticed that when you wear gloves in class, you don't have the grip that you're used to. You don't have the dexterity, the motor control, the fine motor control with gloves than you do without the gloves. And so this is a nice analogy for science being applied to law. Science loses a little bit of its flexibility. In science, pure science, in the lab, you guys, if you've done undergraduate research, you know that you can go in and you can change the procedure, you can change the temperature, you can have quite a bit of freedom in the lab as a scientist. But in terms of forensic chemistry, that freedom is reduced a little bit, because we want to maintain standard procedures and a track record of approved procedures. And we'll see in a second a certain case law that has demanded that science behave or operate within certain restricted parameters. So forensic chemistry is really applied analytical. It's a qualitative and quantitative analysis, and it answers these 3 questions. What is it? How much is it? And how sure are you? Okay, it is the art and skill and science of comparison. So a lot of times we're comparing something at the scene with something at the suspect's house or on a suspect's person or in their possession. And so it's not necessarily that we have to analyze something to the nth degree and answer every fine question about what is it or how much is there. A lot of times we just stop at the point of, is this the same or not? And that's the art and skill of comparison. We also have this hierarchy. We have identifying things, then we classify them. Like in the case of, let's say, blood or a red liquid, the first question is it blood or not? And if it's not, and that seems to be irrelevant to the case, then we don't care what it is. We can just classify it as blood or not blood. Once we classify it as blood, is it human blood or animal blood? And so that's what we mean by classification. And eventually we get to individualization. Is this a particular person's blood, say through DNA typing? And the word forensic in itself comes from the Roman forum. And so that's sort of a shout out to the civilizational benefits of the West. When you have prosperity in the culture, then you could have higher level interests, and one of those higher level interests was a debate over someone's guilt or innocence. It wasn't just a decree of the king, it was actually something that was argued. Is this person the correct person to prosecute for this particular crime? And so that is a high feature of a civilization, to be able to be prosperous enough to have a working judicial system. And it's up to all of us to maintain the integrity of that judicial system. And so in this particular course, we will talk about those high quality standards that are maintained in our judicial system. And then we talk about biology and chemistry. Forensic biology is where you get into the toxicology and DNA, fluids and hair and so on. And we're going to be focused more on the chemistry, trace chemical properties and physical evidence properties. And so we're going to be focusing on these 3 things: the high quality standards, that's the first third of the course, and the chemistry involved, the trace chemical evidence and the physical evidence properties. And so here's a graphical representation of the course. We call it a graphical syllabus. And we have those three parts, the statistics and quality control, which really answer that question, are you trustworthy and is your data trustworthy? And then the chemical evidence, are you competent? And the physical evidence, are you observant? Because it's about trust. Does the legal system trust you and your conclusions? So let's look a little bit at this statistics and quality control piece, since that's the first piece that we're going to be talking about in class. Okay, so remember, this science is operating within the legal requirements of the law. And so what are those legal requirements? Well, one of them is a case, Fry versus U.S. versus the U.S. It's a 293 federal case here. You see at the bottom the reference. And this focuses on general acceptance. Acceptance means it's acceptable to be used in a court of law. And so evidence produced by a scientific analysis is admissible if the techniques are accepted by the relevant scientific community. So do you understand that there could be things that you do in the lab that eliminate the acceptability of that technique? If you have a procedure and you change it completely, it calls out a certain set of solvents and you use soapy water instead of toluene, you've dramatically changed that procedure, and it should not be acceptable in the court of law unless that technique was accepted by the relevant scientific community. And so what is that relevant scientific community? A lot of times we look to peer-reviewed literature. Some good sources are the Journal of Forensic Sciences and the Forensic Science Communications. You can click those links in the PDF and you can go to those sites. Here again are the top 10 publications in forensic science. And so those procedures that are published in these peer-reviewed publications would be at least on their way to being accepted by the relevant scientific community and admissible in a court of law. Okay, how do these scientific communities come up with their correct standard operating procedures? Well, they're these organizations of scientific area committees that are now being organized by the National Institute of Standards and Technology. And here's a nice graphic showing all of the different sort of areas and categories of forensic data and the various committees or the scientific area committees. So like under DNA, you have the biological data interpreting and reporting, you have the biological methods, and you even have forensics, wildlife forensics, because, if you wanted to, say, have a poaching case, you could do DNA typing on the animals. There are also researchers that do DNA typing of pollens. And you have chemistry and physics and crime scene investigations and so on. These committees produce elaborate procedures and process maps. And so here's a process map for firearms analysis put out by the Firearms and Tool Marks Committee. And this is just one panel of, I think it's like a 9-page process map. It's amazing, the detail that they have in these process maps. So you can go to this place that you can search the Organization of Scientific Area Committees for Forensic Science on Google, and you will find this page, and you can go and look at their process maps, and it's fantastic. It's a fascinating thing to kind of get lost in and work your way through. They also have a nice handy forensic science lexicon. You can go in and type in terms that you've heard and get the approved definitions of those terms, and we will use some of those in this course. So that's how we get to the general acceptance of the peer-reviewed or scientific communities. But then we had to extend this. Who makes the decision in terms of whether it's approved or not? Well, Daubert decision settled that question. They established rules of evidence, and even though it's a federal statute, it's being adopted in state courts, and it sets the judge as the gatekeeper. So if you have a new method, the judge will evaluate things such as the error rate and peer review. Of course, he may have advisors that help him make that decision, but the judge is the final, we call him the gatekeeper for admissibility in the court for our analysis methods. Now, most of Fry and Daubert are focused on scientific methods, analytical methods, their admissibility in court. You can always remember the Daubert decision sets the judge as the gatekeeper for admissibility of the methods. And then CUMO extended the Daubert decision to all expert testimony. So that's your thing that you need to remember for CUMO, is that it extends the judge's gatekeeper role to all expert testimony, including those things that may not be scientific. Let's think maybe some of the less data-driven expert witness testimony, say for some psychology profile or something like that. The judge is the gatekeeper for all of those areas for expert testimony, not just scientific analysis methods. And it acknowledges that each discipline, such as psychology, would have its own admissibility standards, and so the judge would be using that to make his or her decision on whether the expert that is being presented for use in the case actually meets the criterion of the experts community. Let's talk also about some of the evidentiary categories that we have. There's inclusive and exclusive evidence. And then there's also, so inclusive evidence would be evidence that includes a suspect. Exclusive evidence would be evidence that eliminates a suspect. And we need both kinds. In fact, it would be wrong to look only at inclusive evidence. You also need to look at evidence that would exclude. Otherwise, you're biasing the analysis towards a particular conclusion. We also have categories of evidence called direct and indirect evidence. Eyewitness testimony is direct evidence. Direct evidence goes through persons and what they see, hear, say, and so on. Indirect evidence requires logic and inference, and a lot of times people call indirect evidence circumstantial evidence. And there seems to be a bias against that. People say, oh, they only have circumstantial evidence. Well, that they are of equal weight. And so juries are instructed to give no difference in weight between direct evidence and indirect evidence. So that you can ignore or just, realize that when someone say, oh, it's just a circumstantial evidence case, that they don't really know what they're talking about. The direct evidence and indirect evidence are given equal weight in the court of law. There's destructive and non-destructive testing, and you'll see in those process flow maps that there's a decision point to say, if I'm going to destroy all of the sample in this analysis, I need to get approval. That's the last thing you want to do is have a piece of evidence, run it through a destructive testing method, and use it all up. And then when they go to look at that evidence again in the future, it's gone. You consumed it all. And so it's best, if you have a destructive testing method, to use a small portion of the sample so that you don't use it all up. And that sometimes is not the case. You have a tiny little paint chip, on a deceased's body. Maybe you can't do particular analyses because it's going to destroy the whole piece of evidence. Evidence is tracked through the chain of custody. A custody form follows each piece of evidence from the forensic photographs at the scene that's bagged and tagged with an evidence number, and it goes in with that case into the evidence locker. And every time it's looked at, that evidence form or chain of custody form follows that piece of evidence from the locker where it's stored into the hands of the analyst, into the lab where they do the work, back in the hands of the analyst, and back into the locker. That chain of custody is probably the most important thing in forensic science, because that's what ties this piece of evidence to the scene of the crime. Let's look now at the chemical evidence. We're really just going to be focused on looking at some of the chemical methods that we use to separate analytes, like liquid extraction and instrumental analysis and drugs. In pharmacology, we have a couple of lectures on pharmacology, what drugs do in the body, but mostly this is the chemistry side of forensic science. And Typically, the flow of a forensic analysis is evidence where a general unknown comes in. We do presumptive tests like wet chemical methods and spot tests, color change methods with drops and so on. And that's the lowest level of analysis, not as robust. And then we have a little bit more of a screening test, extraction and separation. This would be called category B. Again, not as tied to the identity of the substance as we'd like. Think about a chromatogram. A chromatogram, there's a retention time and a peak associated with a particular substance, but it could, coincidentally, any substance could come out at that particular time. That retention time isn't so individual to that particular chemical. It's just a balance between its preference to be in the mobile phase or in the stationary phase. And so the separation technique, like a chromatogram, would be a category B method. But then you get to confirmatory tests and instrumental analysis where you might have, say, an infrared spectrum, which is tied to the very chemical identity of that compound, or a mass spec where it fragments in a particular way that is individual to that particular compound. And so those are the highest, most reliable methods, and so those are category A. And so a lot of times the forensic science community requires at least 2 category A analyses, or a category A plus a couple of category B analyses. And so they have criteria at which you have to meet to say this is heroin, or this is cocaine, or this is methamphetamine. Okay, we'll get into more of that later. We also get into the physical evidence. In the physical evidence, we start talking about the shapes of things and the physical properties of things, like gunshot residue analysis. We look at the shapes of the molten metals that come out of a firearm when it's fired. Or we look at the physical evidence left behind in an arson. Or we look at the color changes and the physical properties and the way they interact with light. And so that's a fun part of the course. We start doing different types of chemistry than you're used to, and hopefully you enjoy it. And then during the whole semester, we have these weekly to-do items of the homework quizzes and the control chart. So the control chart data will be going every day of the semester, or on weekdays. Sometimes, like if you're doing a stock, you'll have data on Monday through Friday, but you won't have data on the weekends, and that's okay. That's not a problem, but it's still a daily collection of data Monday through Friday. And then we see the letter grade criteria, and then down here at the bottom, this is how the points are broken up into the different exams, the control chart, and the homework. So the control chart reports are worth 10% of your control chart grade. You will get a grade for your peer review. And so I will have you review 2 proposals each, or 2 midterm quality reports each. And I will go through to see if your review was specific, if it was criteria-based, if you gave constructive feedback. So I'm going to be teaching you how to peer review. It's not just, here's 2 papers, look at them and say everything looks good or not, check for typos. It's going to actually be, I'm grading to see if you've done a good review. So that will be part of your grade as well. And then the homework quizzes are very similar to PChem. You have some multiple choice and fill in the blank numerical problems, and those will be running automatically every week. Okay, so it's going to be a great semester. Let's look a little bit more about this control chart assignment, because I would really like for you guys to start thinking about what data you're going to track during this semester. So the purpose of this assignment is to learn about continuously variable data versus category data, like digital rounded data. We'll see some of that in a second. They also demonstrate the meticulous skill of monitoring a process daily for 15 weeks, and you'll get to experience the benefits of data-generated action in contrast to calendar-generated action. And what that means is you're not going to do a log entry in your control chart log until your data goes out of control. You will still track everything daily, but the action that you will take will be governed by the data itself. So it's not like you will make a log entry every Monday on a calendar basis. You're going to update your data, and then when the data goes out of control, then you take action, and that's what we mean by data-generated action. So let's look at some of the control charts. This is the kind of control chart you're going to produce. It's going to have a 15-day training period. And we need a training period because we need to see what the standard deviation of your data is. During the training period, it's really not a control chart. You're just collecting data. So we won't make a chart for the first 15 days. So we'll collect data for a full 3 weeks, and then we will use those first 15 data points and calculate the standard deviation and the mean. Once we have the mean and standard deviation, then we can plot the control chart. Then we can plot the mean line, and we can take the mean plus and minus the standard deviation and plot the watch lines. And then we'll add 2 times the standard deviation and plot the action lines. And your data, 95% of the time, will stay within those action limits and be what we call in control. But when it goes outside the action limit, that's such a dramatic difference from the mean that we would say something non-random happened. We call that a special event or a special cause. And so that would cause you to go and investigate. So your data is rocking along, staying within the action limits, no action is needed. But if it goes outside the action limit, then action is needed. And the action in this case would be to go on the internet, or if you're tracking something with your body, to look at your schedule and see what happened, and log that in the quality control log. In this case, we're tracking the flow rate in liters per minute, and you see that it's up and down, but it stays mostly in control. There's only 4 times when this data collection piece went out of control, and so there would only be 4 entries in the data quality log, even though you collected data for 15 weeks. Okay, so you must get my approval for your data choice because some of the data is not going to work well for your exercise, and so that's why I'm making you get my approval before you start tracking the data, because it's no fun to track data for 3 or 4 weeks and then realize it's bad and you have to start over. Okay, so here's an example of a bad choice: tracking temperature, because what we're going to do with as the spring hopefully progresses is that we're going to warm up. Huntsville's going to get warm, and a control chart should have data that doesn't trend up or down. You see that this daily change in flow rate, well, I'll talk about the daily change in a minute. You see that the mean is very close to 0. And some days it's above 0, some days it's below 0, but on average it's really close to 0. That's what you should have for a control chart variable. It doesn't have to be 0, but it has to be a constant number that shouldn't change. Let's say you're going to track your balance and you're going to weigh 1 gram on that balance every day. And it's going to be a little bit above a gram, a little bit below a gram, plus or minus that standard deviation. And it's going to be different every day, because every day you have a slightly different atmospheric pressure, slightly different temperature. Hopefully the weight hasn't changed, but there's lots of little differences every day. And so it should be around 1 gram, but it should be slightly above, slightly below the whole semester. Okay, so temperature is a bad choice because temperature is going to trend upwards as we go through the semester, but daily change will take that slope out. And so daily change in temperature is good. If you're going to track the daily change in temperature of Huntsville, that's fine. Some days we'll have a warm day and it'll be above the average. Some days we'll have a little cold air come in and it'll be below the average. And so it should bounce around 0 change. And so daily change in temperature is good. Now, whenever you're doing daily differences, and this is the same for stock price, temperature, relative humidity, it doesn't matter. If you're going to do daily differences, always take the measurement for today and subtract from that the temperature previous. So it's today minus yesterday. It is not yesterday minus today. And you will lose major points if you get this messed up. Now, why am I so insistent on this? Let's say today was warmer than yesterday. So this difference will be positive. And that's what you'd want, right? If the temperature went up, you want the difference to be positive. If you have this reversed and the temperature goes up, the difference would be negative. And that doesn't make any sense. The temperature went up, but your difference was negative. You see how that's backwards? So you must take the current temperature, the current stock price, the current pressure, whatever you're tracking, and subtract the previous one. And then your differences, the sign of the difference will match what actually happened. And then when you're writing this up in your quality report, this is the way you phrase that. You say the previous day's temperature was subtracted from the current day's temperature. If you get the equation right and you do the Excel right, but you get this text wrong, it's still wrong and you're going to lose major points. Okay. So grammar is important because that is what we're telling in words what we did in actuality. Some people want to track their weight. It's not a good idea, but you could track daily change, and that would, because weight is going to trend. Mine keeps trending up. Nothing I can do, it seems. But tracking the daily change, that will go up and down. So that would be fine. Gas prices are no good because they're rounded to the penny and they're not continuous. And so the continuous statistics that we need, like mean and standard deviation, don't apply well to something that's rounded like that. Okay. So that's what we mean by continuously variable data. So let's look at this control chart. Okay, this is an example of bad data. Can you tell what's going on here? Look at the y-axis. We have daily change in flow rate, and it's either 0, +1, -1, or -2. Can you tell what's going on with this flow meter? It only reads to the ones place. It doesn't have 0.1 or 0.01 decimal places. And so it's unlikely that the flow rate was exactly 1 or 0 or -1, etc. It's more likely that this data is being rounded and we're losing the decimal places. So this is what we mean by discrete data. It's not continuous data. So in that goal that I had earlier to learn about continuously variable data, this data is not continuously variable, meaning there's not a continuum of data points on the y-axis. There's really only 4 options here. And so this is what we call category data or discrete data. And our statistical models, the mean and standard deviation and confidence intervals, they require continuously variable data. So that's why this is not a good source. And this is what you see with gas prices. When people try to drive, they drive by HEB every day and they collect the gas price for unleaded, and you'll see that it'll be, by the penny up and down, and they won't have continuously variable data. Okay, what's wrong with this control chart? Well, look at this is temperature in Huntsville as we go into the spring. You see it goes up and down, but in general it trends upward. And so this data is not in control. If it's a sloping data set, it's not in control. So a control chart should have a source that is constant, because that's what you're trying to detect. If it's constant and you come along and there's a day where it's way off, you know that's wrong, because it should be the same number every day, plus or minus some small band of uncertainty. And when you have a data point that's way off of that constant value, then you know the system is out of control. Okay. So if we took the daily difference, that slope would be subtracted out, and we would have a nice, zero sloping data, and it would be something that we could chart on a control chart. So temperature is bad, but daily difference in temperature is good. And so you must choose a data source that does not slope up or down with time. So even stock prices, those slope up or they may slope down, but if you take the daily difference in a particular stock price, then that's good. It was great. And sometimes something happens to your data, throughout the semester. And that's life. Things happen to your data in the lab too. We had a student tracking Yamaha stock prices when the Japanese had their earthquake, tsunami, and nuclear meltdown. And so the Yamaha price was trucking along just fine. And then I think it was March or April when all of those terrible events happened in Japan, and his price went up and then down and became incredibly volatile. And then he didn't have data for several days because the stock market in Japan closed down as they were dealing with the crisis. So yes, his control chart exercise was unable to be finished for that semester. He still wrote a good report, but I thought it was very interesting. He's tracking something that was in control, and then it went completely out of control and then just quit. So that was actually a fascinating control chart. and he was able to track with his action log the events of that again, earthquake and tsunami and nuclear disaster. So I hope this helps you get excited for the course. I'm excited for the course. We have a huge group of students. I think there's 42 people enrolled in this course. That's the first ever that we've broken 40 for this course. So I'm excited to see you all on Thursday. And I hope you stay warm and stay safe and have a great beginning of the semester. I'll see you on Thursday.